Our next speaker is Max Torke, who is one of our NASA interns.
Hello, everybody. Hope you're having a good day so far. My name is Max Torke, and I just graduated from Sonoma State with degrees in physics and chemistry. And I had the opportunity this summer to work as an intern at NASA's center in Goddard. And what I was working on while I was there is developing a simulator that simulated infrared transmission through a dielectric foam. And as with a lot of the missions at NASA, they start by launching a satellite. So that's how I'm going to start my presentation. We have a satellite, and it's up in space, and there's a lot of considerations when you put a satellite in space. One of these considerations is radiation that's constantly hitting the satellite, and I'm going to be focusing on infrared radiation. So a couple problems with this is it can interact with the detectors. It can heat up detectors, which can cause them to fail, or it can actually be you're trying to detect infrared radiation in your imaging, and infrared radiation from other sources will get in the way. So one way to prevent infrared radiation from causing failures is to cover a satellite with a thin layer of dielectric foam. And this layer can be on the order of 1 millimeter thick to about 10 microns, and that's going to help get rid of infrared radiation. So a dielectric is a electrically non-conducting material, and it's a foam because it's not a uniform material. It's not like solid. It's got kind of clumps and chunks, so it has a very unique structure. So you use this, you can use it as a filter where it allows the transmission of certain frequencies and actually will disallow other frequencies. So, and this happens through the properties of the dielectric, like absorption, reflection, and scattering effects. So a couple applications that were considered during my project is putting it on the ICESat-2, satellite to be launched soon, that has cryogenically cooled detectors where they're trying to detect infrared radiation. And they're using that to image ice shelves and ice crystals inside clouds. So of course the concern is that you're going to get infrared radiation from other sources, and that can be a problem. And it can actually heat the detectors up, which means they'll stop functioning because they have to be cryogenically cooled. Another possible application is the use in satellites trying to detect the cosmic microwave background, such as COBE and WMAP on the bottom right. You can see some spectrums they've gotten of the cosmic microwave background that's kind of indicative of the early formation of our universe. So my project goal specifically was to generate these transmission spectra of the infrared radiation as it passes through a dielectric foam. And the purpose of that is when you're coating this satellite in some thickness of a dielectric, you have to know how thick does it need to be to give you the optimal spectrum. So this spectrum is a measured spectrum from a dielectric called Zytek, and the y-axis is transmission, which just tells you what the intensity of light is able to pass through the dielectric. On the x-axis, you're actually going to see frequency. So at different frequencies, the transmission is going to be different due to a variety of effects, which I mentioned. So the Zytek, as I said, is one of the dielectrics they're considering using for satellites. And it can be used as one of these frequency filters. Zytek specifically is a fibrous, porous Teflon that's composed of very thin fibers of PTFE, or polytetrafluoroethylene. And the way they clump together, they sometimes form these pores that are kind of, they're very important substructures that are going to affect all of these constants that we use, these variables. So I just wanted to quickly discuss the variables that are used in the simulator. The first important consideration is electric permittivity, which has multiple effects. The imaginary, there's a few effects, one of which is the wavelength of the light as it propagates through the dielectric, which is important for if you have interference that's constructive or destructive. And you're also going to see absorption due to the imaginary component of the electric permittivity. And this can also be used to model scattering effects. So next, you need to know about the absorption poles of the dielectric, which, because it's infrared radiation, it's going to be able to be absorbed because it excites rotational and vibrational states inside dielectrics. So in the model, I had to put in variables for the strength, the shape, and the position of these poles and frequency. So lastly, I will quickly discuss what phase decoherence is. So that was the last variable that I put in. So coherence is how well defined the wavefront of light is that's incident on these dielectrics. So there's a few reasons you can get decoherence, which is where you have phase differences between the different photons. One is that the light in space is generally not completely coherent. It actually has some degree of decoherence as it hits the dielectric initially. And the other problem is that you can have surface roughness, which is indicated here in this figure. If you have a really well-defined wavefront that passes through a dielectric, you see it's kind of a rough surface on the right, and it comes out and you get this rougher, less well-defined wavefront. And over time that just becomes kind of a decoherence in phases of this light. So I started, in orange is the experimental data from the Zytek G110, and the simulation. I'm going to kind of take you through the steps that I did to improve the simulator. So I started with a constant dielectric constant rather than a function. So you see it kind of has this oscillating pattern that's called a fringe pattern, where as light passes through a dielectric, it's going to go across, it's going to be reflected off the surfaces, and then eventually it's going to transmit. But you're going to get a bunch of waves that might reflect once, twice, 3 times, so on and so forth. And these can interact constructively or destructively, depending on the frequency of that light. So you get this pattern where it's a fringe pattern. So next I added in scattering effects by changing the dielectric function to have an imaginary component that actually evolves by frequency squared. And you see it slopes down as the frequency increases. And that's just due to the fact that as the frequency increases, the wavelength is shorter, so it interacts more strongly with the pores and the substructure of the dielectric. So lastly, I added in rotational absorption poles. And after adding this in, you can see that the experimental data is now fit fairly well by the simulator. And that was a great success. So I developed this simulator that accurately can model experimental data, and you can use this simulator to determine the optimal dielectric width to coat onto a satellite by just changing the variable of the dielectric width. It's that simple, so it literally takes like 10 seconds. So I wanted to give some acknowledgments. My mentor at NASA, Edward Wollack, thank you for all your experience and expertise. I always enjoyed our conversations. Maybelline and Robert for making this internship possible. And Felipe and Carwan, because they made the experience in lab a bunch of fun. They were my lab mates. And a few people at AIP, Sean Kendra and Courtney, also very helpful throughout this internship. And Peter Rooney was one of the past SPS Congressional Fellows, and he talked to me, and I really appreciated hearing about what he had to say. So, oops. Thank you very much. Yes?
So the 2 little dips in your data, in your simulation, you said it was something about rotations. Can you say a little bit more about what the difference is between the 2 dips? One's skinny, one's fat, and what it might actually, what molecule it might be?
So, the molecule is going to be something, something in the Zytek. Maybe it might be the Teflon, the PTFE. But I can't specifically say what they correspond to. To actually do that, you need a supercomputer to determine how they're going to have these, quantum vibrational states and rotational states. So it's actually the molecule rotating, vibrating. And at those frequencies, it will excite these vibrations or rotations.
Thanks.